So I've got this, the review document that is in Brightspace and I hand out in class, has some highlighted questions. So I'm going to go through and pick those out one at a time. So number one says, which of the following statements is not true of balancing a chemical equation? So I look at the answers and look for any oddballs, like two of the above, none of the above, that type of thing. If they're all unique answers, then I need to run through each one and find the one that is not true. First one says subscripts in the reactants must be conserved in the products. And that is patently false. The only thing that determines subscripts is the name of the compound and or the proper combination of elements in a compound based upon their charges. So that's why it was so important for you to learn how to name compounds and write them correctly so that you would not make this particular mistake. You don't preserve the subscripts. Now, once you write the subscripts into a compound, you can't touch them to balance the equation. So A, in this case, is the only false statement in that list. No, we're not going to do two. Notice I crossed out two because somehow this question snuck in and it incorporates ideas, concepts that we haven't covered yet. So we're going to move on to three. Okay. When the following equation is balanced using the smallest possible integers, what is the number in front of the substance in bold type? So, if you become proficient at balancing equations, some of these you can do without even using my budget method. But I'm going to use the budget method here the first time just so that the procedure is explained again. Right? So we have that compound, we have water, and it yields H3PO4. And you remember from naming compounds, starts with hydrogen, it's an acid, assuming it's in aqueous solution, and from the looks of the equation, it is. So this would be phosphoric acid, and then HCl would be hydrochloric acid. Okay, so our budget method says we pick out the elements P, Cl, H, and O. And one of the hints that I gave you, the tricks, is if you have a polyatomic ion on both sides and it's not broken up or modified in any way, you can use it as a balancing unit, but it only occurs on this side, not on that side. So we have to use individual elements to balance this equation. So now you do your tally: phosphorus, 5 chlorines, 2 hydrogens, and 1 oxygen. On this side, we have 1 phosphorus, we have 1 chlorine, we have 4 hydrogens, and we have 4 oxygens. Okay. The other hint I gave you was if you have an element by itself as a reactant or product, leave it to last, because changing the coefficient of that one reactant or product is not going to affect the others. We leave it till the end, but we don't have that case here. So when in doubt, just start at the top. Right? If we go to chlorine, we say we need 5 chlorines on that side. So I'm going to put a 5 here. And that makes 5 chlorines, plus it makes 5 plus 3 is 8 hydrogens. Okay. Now, if we move to hydrogen and we need 8 hydrogens on this side, it only occurs in one place. So a 4 in front of that would give you 8 hydrogens. And reassessing the oxygens will give you 4 oxygens. 1, 5, 8, 4. This equation is balanced. And the coefficient in front of hydrochloric acid is 5. All right. Let's move on to number 4. All the following are clues that a chemical reaction has taken place, except, so we're looking for the one that's not a clue. A solid forms. Is that a clue? Yeah, solid formation is a clue that a reaction has occurred. The reactant is smaller. That doesn't mean that a reaction has occurred, and that's not one of the clues we discussed. So this one is questionable. It's probably false. So test-taking technique, we're going to, by process of elimination, find all the ones that are clues, and then the one that's left over is the answer. Bubbles form. Oh, yeah. Formation of a gas. How about D? A color change occurs. This one is also somewhat questionable. A flame occurs. Yes, that's heat. Okay. So between B and D, we want to decide which one of those is the most likely. Well, we discussed color change as a possible indicator of chemical reaction. Not that the color becomes lighter or darker. That could be a physical change, simply dilution or concentration. But we didn't talk about reactant as smaller because macroscopically, what you see happening, what you hear, what you feel in terms of heat, we did discuss heat, but that's not mentioned here. Except for a flame. Yeah, a flame occurs. That's true. We were talking in terms of clues, physical clues that we could test with our own senses. You can't determine whether a reactant is smaller in just any reaction. Now, it's possible, but it's not, it requires a special technique, which is characteristic of the reaction you're studying. So that would be the worst answer would be this one. And this one, it would be a better answer. So by process of elimination, we find that reactant is smaller is not a good clue because you can't detect it with your senses necessarily. Okay, number 5. When the following equation is balanced using the smallest possible integers, what's the number in front of the substance in bold? So we've got aluminum. Okay. We got Fe3O4 producing iron plus, well, they put Al2O3 first. Let's do that. Al2O3. Then iron. Okay. And we want this one right here. It's possible that we could balance this one without the budget method. But I'm going to use the budget method now simply because we need practice. So we have aluminum, we have iron, and we have oxygen. 1 aluminum, 3 iron, 4 oxygen, 2 aluminum, 1 iron, and 3 oxygens. Okay. Right off the bat, we see an even and an odd. This would be a problem. We're not going to start with oxygen. So why don't we start with aluminum? Well, if we start with aluminum, then we have to break that rule. We don't have any choice. It's either aluminum or iron. So let's just go with aluminum. So if we put a 2 here, that changes that to 2. And if we put a 3 over here, that changes that to 3. But now the oxygens are not right. So, you know what? Let's go back. I'm going to try a different tactic. Okay. Let's see. This was 1, 3, 4, 2, 1, and yeah, 3 oxygen. Okay. Let's use the one trick that we haven't talked about yet. Cross multiplication. We see oxygen in one place on this side and one place on this side. If we take that 3 and put it over here, and take that 4 and put it over here, that gives us 12 oxygens on reactants and products. Now let's go to the aluminum and iron. So in this case, we've got 8 aluminum there. And this is also 8. And then iron has been changed to 9. So let's put a 9 on this side. There we go. Now we're balanced. So the trick was oxygen occurs in only one place on the reactant side and one place on the product side. And if we use the subscript as a multiplier, as a coefficient on opposite sides, then we can get the oxygens to balance. And from that point on, we have aluminum and iron separate elements. They can accept any coefficient we want without affecting the others. All right, number 6. I think that one's gone. Try another one. Which of the following statements about chemical reactions is false? So I don't see any squirrely ones in there. We have to look at each one. A, B, C, D, and E. All right, is A true? In balancing a chemical equation, all subscripts must be conserved. I think we've attacked that one already, right? Subscripts of compounds, right? Though you don't conserve the subscripts. The prime directive of balancing an equation is that you have the same number of atoms of each element on both sides of the arrow. And in order to get there, first you have to write the correct compounds that are in the equation. If they're given to you, fine. If they're only named, then you have to convert the name into a formula. But A is false. So the rest of them should be true. The subscripts in a balanced equation tell us the number of atoms in a molecule. Yeah. When one coefficient is doubled, the rest of the coefficients in the balanced equation must be doubled. The key there is the balanced equation. Once the equation is balanced, then the ratio of each of the atoms in the reactants and products, that ratio is fixed unless you multiply. And if you multiply, everything in the equation must be multiplied by the same number. That's a simple math principle there. You can do that to a math equation also. Let's see, D, an individual coefficient in a balanced equation is meaningless. An individual coefficient in a balanced, well, yeah, because you have to compare numbers of atoms in the entire equation. And just one coefficient doesn't tell you that. E says the phases in a chemical reaction tell us the nature of the reactants and products. Well, yeah, it does. All right, so the rest of these are true. And A is false. Now let's go to 7. When the following equation is balanced using the smallest possible integers, What's the number in front of the underlying substance, in front of oxygen? Okay, let's write this equation up and then I will say one thing about it. This is a gas, oxygen is a gas, and we always get carbon dioxide water. Okay. What type of reaction is this? Right, we talked about classifying reactions. It's got oxygen as a reactant. This is a combustion. And all combustion reactions are oxidation reduction reactions too. We transfer electrons in the process. So we'll go from there. We got to balance this equation. We're going to use the budget for this one. Let's see, carbon, hydrogen, and oxygen. That's it. So 2 carbons, 6 hydrogens, 2 oxygens. This side, 1 carbon, 2 hydrogens, and 3 oxygens. Now notice we have an odd and an even and an odd. But the temptation to use the cross multiply trick can't be done here because oxygen occurs in 2 different places. So we're going to hold oxygen out anyway because it's a single element. And we're going to start with, say, carbon. Let's try carbon first. So if we put a 2 here, that changes that to 2, and it also changes this to 4 plus 1 is 5. Right? Now we got 2 prime numbers to deal with. How about hydrogen? How do we get hydrogen? Well, we got 6 on this side. So if I put a 3 here, that gives me 6 hydrogens. But now we have 3 plus 4 is 7. We got another prime number. So now how do we get 7 oxygens on this side? We use the fraction trick. If we say 7 halves, that will give us 7 oxygen atoms, right? Because we're taking a half of an oxygen is 1 oxygen, times 7 is 7 oxygens. But we want the simplest whole number ratio. So now we have to multiply. This is a balanced equation, but we want the whole number. So we're going to multiply by 2 because 2 will cancel that 2, right? And leave us with 7. And we'll put a 2 here. We'll put a 4 here. And we'll put a 6 there. And we're balanced. And in front of the oxygen, the number is 7. All right. How about what's the coefficient in front of water for this reaction? Okay, let's try this one. Balancing these equations is not something that you can do intuitively. You need to follow the method. In the beginning, stick to the budget. Later on, as you get experienced balancing equations, you can develop sort of an intuition about where to start or what tricks that might work. But for now, you're learning the method. All right, so we got Al2O3, which is a solid, and then we react it with sulfuric acid. All right, and we're going to get aluminum sulfate. Three. And then water. Let's see, this is solid. No, aqueous. This is aqueous. And then water. Okay, we're looking for that coefficient. All right. So, do we have sulfates on both sides that were not changed? Yeah. We got sulfate here, sulfate there. And we'll have some oxygen separate from those sulfates. Believe me, it works. So we got aluminum, we got oxygen, we got hydrogen, and we got sulfate. Okay, so let's do our tally. 2 aluminums, 3 oxygens, 2 hydrogens, and 1 sulfate. 2 aluminums here. Yep. Let's see. Oxygens, 1. Hydrogens, 2. And 3 sulfates. Okay. We don't have any elements to hold out to the end. So aluminum's okay. We could go to oxygens. Right? If we went to oxygens, I'll tell you what, let's go to sulfate first. 3 on that side, we need 3 on this side. And that makes 6 hydrogens. There's an intuition that I'm using here. I suspect that sulfate would be best to go first. So now we have 6 hydrogens on this side. We need 6 on the other side. Right? So 3 here gives us 6 hydrogens. And it also gives us 3 oxygens. Okay? And we're balanced. Right? We're balanced. So the answer to this one is 3. Next is 11. When the following equation is balanced using the smallest integers, what's the number in front of the substance in bold? In front of the hydrogens. Okay. This one might not be too difficult. We've got 10. Right? You know that because you've memorized the symbol. We've got sodium hydroxide because you learned how to name that compound. And on this side, we have Na2, excuse me, SNO2, which is a polyatomic ion. This is stannate. So sodium stannate. Okay, so we're looking for the coefficient for here. All right, so we got 10, got sodium, got oxygens, hydrogens. 1, 2, 3, 4. Yep. So we've got 110 on this side, got 1 sodium, 1 oxygen, and 1 hydrogen. And over here we have 1 of the 10, 2 sodium, and oxygens we have 2, and hydrogens we have 2. Okay. Sometimes I check myself, just add up. 1, 2, 3, 4. 1, 2, 3, 4. 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so I've accounted for all my atoms to start with. Now, where do we begin? Well, both hydrogen and tin are elements. We'd like to hold those to the end if we can. So hydrogen and tin, we look at sodium and oxygen. Right? We've got 2 sodiums and 2 oxygens. So if I put a 2 here, that gives me 2 sodiums, 2 oxygens, and 2 hydrogens. And guess what? We're balanced. It was that simple. So the coefficient in front of hydrogen is what? It's 1. Remember what I said early on. If there's no number here, that doesn't mean there isn't one. If the symbol's there, there's at least 1. And we don't write the 1. Right? That would be redundant. So the coefficient is actually 1. All right, there's some repetition in practice. Right? You can do all that practice. We're going to go down to 24. All right. When the following equation is balanced using the smallest possible integers, what's the number in front of the underlying species or substance? Okay, we got lead solid. We got silver nitrate in solution. And what type of reaction is this? It's a single replacement. The lead replaces the silver. So we got this lead and nitrate. There are two of them. So what happened to the lead, right? It was neutral on this side. What's the charge on this side? Well, nitrate's a 1 minus. We got two of them, so this has to be a 2 plus. Right? You don't need to know that to solve the equation. I'm just throwing it in there for giggles. And then silver. Now, silver is a solid. Nitrate, we've left that out. Lead 2 nitrate is soluble. All nitrates are soluble. That's one rule that you can rely on. Okay, now we're going to balance, and we're looking for the coefficient here. So we have nitrates on both sides. We can use that as a balancing unit. That means we have lead, silver, and nitrate. That's it. We have one lead, we have one silver, one nitrate. We have one lead, we have, silver. We have one silver and two nitrates. Okay. So if we want two nitrates on this side, we need a 2 here. Right? So that gives us 2 silvers and 2 nitrates. And now to balance it, all we need is that coefficient. And the balanced equation puts a 2 coefficient in front of the silver nitrate. There's another one that snuck in there, and I had to cross it out. We haven't got to that yet. That's coming up soon. Let me see. We've got a lot of practice balancing equations. Okay, this one, this type of problem is multi-step. The first step is to write the compounds correctly. All right? So, the balanced equation starts with iron 3 oxide, 33. And get a better marker. Okay, iron 3 plus, because the name says it has a 3 plus charge, right? Roman numeral 3. Oxide, okay, which is a 2 minus. So we have a 2 here and a 3 there. Okay. Then we're going to react. I put the phases in here because I know what they are, but you don't have to do that to balance the equation. Next one, carbon monoxide. All right, this is a type 2 compound because the metal has possible multiple charges. This is a type 3 compound because it's a non-metal. So when we say carbon monoxide, we know exactly how many of each element is there. One of this one, one of that one. Then the products are iron metal and carbon dioxide. Okay. And what are we looking for? The entire balanced equation, right? we have to write each element up here. There are no polyatomics. So we have iron, oxygen, and carbon. We have 2 irons, 4 oxygens, and 1 carbon. And we have 1 iron on this side. We have oxygens, 2 oxygens, and we have 1 carbon. Okay. So how do we get 4 oxygens on that side? Right? Iron's an element, so we're going to hold it till last. Oxygen, then, we need 2 here. That gives us 4 oxygens and 2 carbons. Right? Let me see if I did that right. Yep, 4 oxygens. That's 2. These are 2 carbons. Okay. Now we need another. Let's see. Yeah, we need 2 carbons on this side. Uh-oh. What's that going to do? If we do that, then that gives us 2 carbons, but now it has 5 oxygens. All right, so this one, I think, is going to need some let's see. Can we work around this one? What if we need an even number? So if we were to bump this up 1, what would that do? The carbons would take care of themselves because the 3 here and the 3 there would be the same carbons. But that would be 3 plus 3 is 6, and then 3 times 2 is 6. But what we're trying to do is, we see that this one is a prime number, right? That's not going to do. And there's no way to make a single coefficient fix the problem, right? Unless we say something like this. Let's say we put a 3 here. What does that do? Well, it makes 3 carbons. And it also makes this one 6 oxygens, which allows us to go even, right? And 2 times any number is an even number. So now if we put a 3 here, then we get 6 oxygens and the carbons line up also. Right? And then iron, of course, we need 2 here. So that one's not obvious on its face, but it can be done. This takes a lot of practice. And what ifs? Oftentimes when you try to balance an equation, you might find yourself going down a rabbit hole and you have to come back out and start over again. Try a different tack. That's just the nature of the beast. All right, we got some others there. Got some there. Lots of good practice. Let's try this one. 39. Let's see. Silver. Okay, in this case, you're given the unbalanced equation, which is nice, right? Silver nitrate. All right. That could be aqueous. And then calcium chloride, which is aqueous. And then we have, I don't want to put the answer up there yet. Silver chloride, solid, plus calcium nitrate, aqueous. Okay. In this case, we do have some polyatomic ions that are same on both sides. We actually only have one, nitrate. What type of reaction is this? Well, it's a double replacement in the first place. Silver swaps with calcium. So we have calcium nitrate, silver chloride. It's also a precipitation reaction because that's solid. We have two solutions we put together and they make a solid. So we have two types going on here. All right, if we want to balance this, let's see if we can balance it without the budget. These precipitation reactions are usually fairly well behaved. So we find, what do we have? We have two chlorines here and only one there. And we have one nitrate and two nitrates on that side. So let's put a 2 here. That gives us two chlorines. It also gives us two silvers. So if we put a 2 here, that gives us two silvers and two nitrates. Still one calcium, and two nitrates. That's a balanced equation. All we needed was a 2 there and a 2 there. Some of these equations, you can do that without going to the trouble of budget. This one's going to take a little work, I do believe. Number 40. See if we can stump the instructor. Even though we got the answer there, I got to show you how to get there. 40. Okay, we're starting off with magnesium nitride. Okay, and water. And we end up with ammonia plus magnesium hydroxide. Stop. So technically, I guess we could say this is well, it's not really a precipitation reaction because we've already got a solid. Right? We're not making a solid from nothing. Okay. All right. So let's tally up what we've got. Magnesium, nitrogen, hydrogen, and oxygen. 3 magnesium, 2 nitrogen, 2 hydrogen, and 1 oxygen. And on this side, we have 1 magnesium, 1 nitrogen, hydrogens. We got 3, 4, 5 hydrogens, and 2 oxygens. Remember, that subscript has to propagate through. All right. So, I don't see anything special here that could help us. So let's start at the top and see where that gets us. Magnesium is 3, so let's put a 3 over here. That's 3 there. Now that changes the hydrogens and oxygens. 3 times 2 is 6 oxygens. Right? And 3 times 2 is 6 hydrogens. Okay. All right. How about nitrogen? We got 2 on this side and 3 on that side. Oh, no, 1 on this side, excuse me. 1 on that side, 2 on this side. So if I put a 2 over here, that's 2 nitrogens. Changes the hydrogens. This is 6, and this is 6, so we have 12 hydrogens. Okay. Now on this side, we've got a water molecule. Look at the ratio. Did I count that right? Hydrogens. No, I put it in the wrong place, didn't I? Yeah, I put it in the wrong place. This is 6, and this is 12. 12 hydrogens. Still got 6 oxygens, yes. And we've got 6 plus 6 is 12 hydrogens. Okay, now we got it in the right place. Notice the ratio. 2 to 1 here. 12 to 6 is 2 to 1. So if we put a 6 in front, that gives us 12 hydrogens and 6 oxygens. And we're balanced. All right. More examples. Yeah. More and more examples that I'm currently skipping, but you don't have to. Need practice. How about, let's see, yes, find another one. How about this one? Okay, this is a good one. This is an acid-base reaction. Notice hydrochloric acid and calcium hydroxide, acid-base. So what do we expect from an acid-base reaction? The product should be the salt. The cation from the base and the anion from the acid make a salt, and the other product is water, always. All right, 51. So we've got hydrochloric acid plus calcium hydroxide yields calcium chloride, which is soluble, plus water. There we go. Okay. Acid-base reactions are fairly well behaved also. We've got 1 chlorine on this side and 2 on that side. So if I put a 2 here, excuse me, that produces 2 hydrogens, and 2 hydroxyls. When you put a hydrogen and a hydroxyl together, you get water. So 2 of these and 2 of those makes 2 waters. That means we need 2 waters on this side. And if you count them up, you've got 2 plus 2 is 4 hydrogens. 4 hydrogens. You've got 2 oxygens. 2 oxygens. We've got 2 chlorines. And we've got 1 calcium. And we're balanced. Now, you're welcome to do this by the budget method, right? Until you get comfortable with these types of reactions. But this also works, and it's quicker. Once you realize what type of reaction you have, then you can limit yourself to certain steps that get you to the end product. Let's see, how about 53? This one might be a real challenge. Get a fresh marker. 53. All right, we've got sodium borohydride. Okay. We've got boron trifluoride. And products are sodium borofluoride. Sodium borofluoride. And diborane. Okay, so we are going to have to use the budget method on this one. We got sodium, boron, hydrogen, and fluorine. 1 sodium, 2 borons, 4 hydrogens, and 3 fluorine. On this side, we have 1 sodium, boron. We have 3 borons. And we have 6 hydrogens. And we have 4 fluorines. Let's see if I counted them right. That's 7, 8, 9, 10. 1, 2, 6, 7, 8, 9, 10. This is 12, let's see, 10, 14. 1, 2, 6, 7, 8, 14. Okay. Now, the question is, where do we start? Can we use any type of one of the tricks? Well, we got boron in 2 places. Sodium's in 1 place. Fluorine is in 1 place. So I'm going to try the cross multiplication trick. Okay. So if I take this 4, put it over here, and this 3 and put it over here, what does that do for us? Well, now we still have 1 sodium. We have 5 borons, hydrogens. We still have 4 hydrogens, and we have 4 times 3 is 12 fluorines. On this side, we still have 1 sodium. I have 3 sodiums, excuse me. We have 3 sodiums. We have 3 plus 2 is 5 borons. Hydrogens. We have 6 hydrogens still. And we have fluorines, 12 fluorines. Okay. Now, we need 3 sodiums. So if I put a 3 here, what does that do? Well, it says 3 sodiums, of course. It says 3 borons plus 4 is 7 borons. All right. And it says 12 hydrogens. Okay. So on this side, we've got, let's see, 3, okay, boron. We need 7 borons on this side. We've already got 3 here. So if I put a 2 here, that makes 4 plus 3 is 7. And it changes the hydrogens to 12. Okay. And we're balanced. So the trick to this one was to see that we could use the cross multiplication trick, because the fluorine only occurs in 1 place on the product side and 1 place on the reactant side. And that set us on the right path to finish it off. All right. Next, got lots of practice. All right, let's try this one. This is a oxygen combustion reaction, oxidation reduction reaction. We want to balance this equation, number 61. Oops. All righty. Let's try another 61. Okay. So we're starting off with C3H7OH. That's propanol. Right? C3H7OH. We separate these H's because this tells us that this is an alcohol. Then we have, I'm going to leave the states out. They just get in the way. O2. And we get carbon dioxide plus water. Okay. So we're going to hold oxygen out to last, but we do need to tally the rest of them. Tally all of them. Carbon, hydrogen, oxygen. 3 carbons, 7, 8 hydrogens. 1 and 2 is 3 oxygens. And 1 carbon, hydrogens 2, and oxygens 3. Okay. With the combustion reaction of a carbohydrate like this. Yeah, it's a carbohydrate. Usually the best place to start is carbon. So we have 3 on this side and 3 on this side. That changes the oxygen to 6, 7. Okay. And then we come to the hydrogen side. We need 8 on that side. So if we put a 4 here, right, that makes 8 hydrogens, and it changes the oxygens to 6, right, plus 4 is 10, correct? 4 plus 6 is 10, right? So the last thing we need to do is to have 10 oxygens on this side. Well, we've got 1 already, right? So we need 9. We need 9 oxygens here. Okay, that gives us 10. It's easy to miss this 1 oxygen in here when we're trying to balance because we see that oxygen by itself. Don't forget to look for other oxygens, just in case. Now that we have a balanced equation, we can get rid of the fraction. Right, 2 there, that's gone. And this is 6, and this is 8. Right? So our coefficients are 2, 9, 6, and 8. All right, here's one where we have to write the compounds from the names again. Number 62. All right, so reaction is between iron 3 oxide. We have iron and we have oxygen, which is a 2 minus, and this is the 3 plus. So we have a 3 here and a 2 there. Okay, and the next one is, okay, we did have carbon monoxide and carbon dioxide in the previous one, but I think it was a different mix of reactants. So this is carbon monoxide. And what we have left over is iron 2 oxide. That's it. That's all you need, right? 1 and 1. And then carbon dioxide. Okay, now we're going to balance. Iron, oxygen, and carbon. So we have 2 irons, 3, 4 oxygens, and 1 carbon. On this side, we have 1 iron. Oxygens, we have 1, 2, 3. And carbons, we have 1. Okay? We don't have any elements to hold out, so I just start at the top. All right, we needed 2 irons. That means 2 plus 2 is 4 oxygens. All right? Okay, and we're balanced. That's it. That's all it took. All right, let's see here. Lots of practice. We're making hydrogen gas out of that one. How about this one? Here's another combustion reaction with octane, CH18. That's gasoline. Right? Most of gasoline is octane, except for maybe up to 10% ethanol. That's a different reaction. So when you fire up your engine, you have multiple reactions proceeding. All right, so we have CH18 for 68. Plus oxygen yields carbon dioxide plus water. Okay. Budget, carbon, hydrogen, oxygen. 8 carbons, 18 hydrogens, 2 oxygens. 1 carbon, 2 hydrogens, and 3 oxygens. Okay. So let's start with the carbon. 8 carbons. That means 16 plus 1 is 17 oxygens. Right? And then hydrogens, we need 18 hydrogens. So if we put a 9 here, that's 18 hydrogens, but it changes the oxygen mix. 16 plus 9 is what? 16 plus 9 is 25. Right? Now we can do the fraction trick. 25 halves. And get rid of the fraction. Right? So we have a 2 here. We have 25 there. We have 16 here and 18 there. So our coefficients are 2, 25, 16, and 18. All right. Okay. All right. 73. An aqueous solution of ammonium carbonate is allowed to react with aqueous solution of nickel 2 chloride. Identify the solid. It tells us there's a solid there. So you can take your chart, this chart, right here. Take that chart and find out what your solid is. So what are we reacting here? Solution of ammonium carbonate. Ammonium carbonate. Okay. And nickel 2 chloride. We got nickel 2 plus and chloride minus. So these are both soluble, right? So we're looking at a combination of this cation and that anion, right? Nickel 2 plus and carbonate 2 minus. So that's one compound. The other is ammonium chloride. All right. The rule says that all ammonium salts are soluble. So we look up nickel carbonate, right? We go here, we go across the top, we find nickel right here. We go down to carbonate. Sure enough, it's grayed out. This is your solid. And this is written correctly. NiCO3, 2 plus, 2 minus. Right. So in this case, B is the answer. It's not marked, but I want to do 74 while we're here. Students tend to get confused. Maybe they just haven't studied enough to know the difference, to detect what type of reaction we're dealing with. So this 74 has magnesium solid plus oxygen yields magnesium oxide. That reaction is very bright. You don't want to look straight at it because it gives out a lot of ultraviolet light and it can damage your eyes. But this is a combustion reaction because of the oxygen. It's also a synthesis because you're taking 2 elements and making a compound out of them. And it's an oxidation reduction reaction. Now let's look at our choices. We have synthesis, oxidation reduction, and combustion. Oh, E got chopped off. There it is. E, it missed a page there. E says A through C are all correct. That is true. A, B, and C are all correct. It's every one of those types. All right, let's go to 75. Why do we need to learn this? Types of reactions? One of the reasons that comes to mind is when you identify a type of reaction, it shares common characteristics with other reactions of the same type, like combustion reactions. Combustion reactions are all exothermic. They give off heat. They also consume oxygen. So if you combust something in an oxygen atmosphere and you have enough of it, you'll suck out all the oxygen. Okay, 75. A substance that, when dissolved in water, produces a solution that conducts electric current, very efficiently is called, it's an electrolyte, but it's also a strong electrolyte because of that word, that phrase, very efficiently. So D is the correct answer for this one. It's a strong electrolyte. And this is what's called an operational definition. We define the nature of the compound by what it does. Okay, 76. The equation 2Ag2O, or silver oxide, yields silver and oxygen. What type of reaction is that? Well, we're taking a compound and we're breaking it apart, right? It's not a synthesis, it's the opposite of a synthesis, which is decomposition, right? It's definitely that. Also, we're making neutral elements out of the compound. That rule of thumb says this is also an oxidation reduction reaction. So B, and C are both correct. It can't be a decomposition and a synthesis at the same time. So that's out. And it's not a combustion because oxygen is on the product side, not on the reactant side. So B and C are correct. Two of these are correct. Let's see. In what type of reaction is water always a product? That's simple. Always acid-base reaction. Okay. Acid-base reaction gives you water every time. Let's see. Let's look at 80. The factors that most commonly cause chemical reactions to occur are all the following except cause a chemical reaction to occur. All right. A decrease in temperature? Actually, an increase is more likely. So A is probably the false one. B, transfer of electrons, definitely. Formation of water, oh, definitely. Formation of a gas, oh yeah. Formation of a solid, yep. So the one that doesn't fit is a decrease in temperature. Well, 81, while we're here, let's classify this reaction. Methane plus oxygen yields carbon dioxide and water. That's oxygen. On the reactant side, that's a combustion reaction. It's also oxidation reduction. What are our other choices? Decomposition? Nope. Synthesis? Nope. Only two of these. Two of those are correct. The scientist who discovered the essential nature of acids through solution conductivity studies is Arrhenius. Arrhenius was working on conductivity experiments with acids. And that's when he proposed his definition for acids, because he recognized that conductivity of acids increased as the dissociation of the acid increased. So a weak acid would produce very little conductivity, a strong acid would produce more, and he reasoned that the culprit was release of protons into the solution, along with anions that would be left behind. That was Arrhenius. Svant. It's a difficult first name to pronounce. Svant Arrhenius. Okay, 84. Let's see. I'm going to have to get a fresh marker. Yep, get a fresh marker. All right, 84. An aqueous solution of ammonium sulfide is allowed to react with an aqueous solution of barium chloride. What is the coefficient of the solid in the balanced equation? All right, this one takes some effort. This is like a multi-step equation. First thing you have to do is write the compounds correctly. You're told the reactants, but you're not told the products. But you are told that there is a precipitate, a solid form. So that will help you write the products. Ammonium sulfide. Ammonium, right? And sulfide is a 2 minus. So this ammonium needs a 2. And that's reacting with what else? Barium chloride. Okay. We looked that up on our periodic table, found barium is an alkaline earth. Right? So it has a 2+ charge. Chlorine is a halogen with a -1. That's why I can write it that way. Now what happens? Well, double displacement. Barium combines with sulfur. So barium is a 2+. That's a 2-, so we only need one of each. We look it up in our chart, and we find that this is a solid. Then we have ammonium combining with chlorine. Right? And that is soluble. Okay? So now we've written our compounds correctly. We need to balance the equation. All right. Ammonium's on the same, both sides. Sulfur, barium. We might be able to balance this one without the budget method. Let's see. We need 2 ammoniums on this side. Right? So that's 2 ammoniums. We got 1 sulfur, 1 barium, 2 chlorines. That's balanced. So the coefficient in front of the solid is 1. Right? That's it. It's that simple. The real trick to this one is writing the compounds correctly and knowing what the products will be in a double displacement reaction with a precipitate. All right, let's see, I've marked off 85. The equation appears to be balanced. Is an oxidation reduction reaction true or false, and why? It is true. The rule of thumb says it's a combustion reaction, so it's automatically an oxidation reduction, but that's not one of our selections. So let's write the equation and reason it out. Let's see, we have 7 yields carbon dioxide and water with coefficients of 4 and 6. Okay. Yes, this is an oxidation reduction reaction. It is true. So A, B, and C, and E, those are all possibilities. D, we throw D out. So what happens to these elements? Well, we know that this one is 0. Oxygens, the rule is that oxygens are -2. So this hydrogen has to be a +1 to balance the charge. This one has to be a +4 because 2 times 2 is -2, -4. That one has to be a +4 to balance. And this one is a +1 for hydrogen, which means 6 pluses, right? We have the need for 6 minuses, but we got 2 carbons, so each one of these is a 3 minus. Okay, now we can say what happens. The carbon, what does it do? It loses electrons, but how many? Well, to get to 0, it loses 3. And to get to +4, it loses 4 more. So it loses 7. We have a loss of 7 electrons per carbon. All right. How about the oxygen? It goes from 0 to a 2 minus in both cases, right? So it gained 2 electrons per oxygen. Now, to answer the question, we don't need to balance that part of it. We could, but we don't need to. To answer the question, the carbon is what? It loses electrons. Oil, oxidation is lost. Carbon is oxidized. So that means it's either B or E. And the hydrogen is reduced. Carbon is oxidized. No, hydrogen is not. Hydrogen doesn't change. Oxygen does. Oxygen is reduced. Carbon is oxidized. That's E. Okay, 86. And let's make room for 86. Yeah, we got time. We can probably finish up today. '86. Okay, how many electrons are transferred in the following oxidation reduction reaction? So we've got zinc and silver nitrate. 2 of those in aqueous solution. Then we have zinc nitrate with a 2 here and silver. And 1, 2, and 1. Okay. So the number of electrons that are transferred. This is 0. This is 0. Oxidation state. Nitrate is -1. Silver is always a +1. Okay. So zinc, in order to find out what the charge on zinc is, because this is a type 2 compound, zinc could have multiple charges. Yes, zinc could either be 1 or 2. In this case, it's 2 plus, and that's 1 minus. Now this nitrate didn't change. Nitrogen and oxygen did not change. But the zinc went from 0 by losing 2 electrons per zinc times 1 equals 2 electrons. Okay. Silver gain 1 electron will make it neutral. Gain 1 electron per silver times 2 silvers equals 2 electrons. So how many electrons are transferred? 2. All right. 89. An aqueous solution of sodium carbonate is allowed to react with an aqueous solution of magnesium chloride. The complete ionic equation contains which of the following species when balanced? Standard form. All right, so the first thing you do is write your compounds correctly. Aqueous sodium carbonate. Sodium and carbonate is a 2 minus. This is aqueous. So that has to be 2 to balance the charge. What's the other reactant? The other reactant is magnesium chloride. Magnesium is an alkaline earth. It has a 2+ charge. Chlorine is a halogen with 1 minus, so we need 2 of those. And that's also aqueous. So what does it produce? Well, this is double replacement. Right? Magnesium carbonate right? 2+, 2 minus, that's it. And we look it up in our chart, and this is a solid. This is our precipitate. And then sodium chloride is obviously aqueous. Okay, so now we need to balance it. We need 2 sodiums on that side. So I'll put a 2 here. That gives us 2 chlorides, 2 sodiums, 1 magnesium, and 1 carbonate. That's balanced. Okay, the complete ionic equation in aqueous solution, this is sodium, 2 of them, aqueous. And then carbonate is also aqueous. Only 1 of them is needed. Then magnesium, 2+ aqueous, and 2 chloride ions, aqueous. All right, the solid stays solid. And then we get 2 sodiums plus 2 chlorides in solution. That's the complete ionic equation. Now, which one of these fits? Well, Na plus doesn't work because it doesn't have its coefficient. 2CO3, 2 minus. CO3, 2 minus, there's only 1 of those. All right, so that's not it. Magnesium 2 plus. Yes, that's there. It's aqueous, and there are 2 of them. So C, let's see, complete ionic equation. Which of the following species? Which of the following species? Well, oh, I missed that. There's a 2. There's a 2 there. There's not a 2 here. Okay, so C is not right. C is wrong. Chloride, Cl minus is not right. There's a 2. E is correct. E is your best answer. Considering both the ion, its state, aqueous, and its coefficient. That term is present in the complete ionic equation. Let's see, how about 96? An aqueous solution of ammonium sulfate is allowed to react with an aqueous solution of barium nitrate. Identify the solid. All right, in this case, I think one of the slides in our presentation of the material had it this way: ammonium sulfate. So we have ammonium here, we have sulfate here. Okay. Then we also have barium nitrate. Barium is an alkaline earth. Nitrate is a polyatomic ion. And then we put them together. Well, ammonium sulfate, we already know that's soluble, right? Because it's in solution. Barium nitrate is soluble also. What we want is barium sulfate and ammonium nitrate. Ammonium nitrate is soluble because all ammonium salts are soluble, all nitrate salts are soluble. So this one is aqueous. The only one left is barium sulfate. And if we look it up, barium sulfate is Ba 2+ with the sulfate 2-. There's your solid, barium sulfate. '97. The reason I put this one in here is because it has a picture that may be difficult to understand what the author's getting at. So which drawing best represents mixing aqueous calcium chloride? Calcium chloride, aqueous, mixed with potassium sulfate. Okay. Sulfate. When they're mixed in stoichiometric amount, neither reactant is limiting. All right. So this is the reactant side. This is the product side, where we have potassium chloride, which is aqueous, and calcium sulfate, which is solid. Okay. So if we balance the equation, we need 2 chlorides. That gives us 2 potassiums, 1 calcium, 1 sulfate. That's all we need right there. Okay, what does it look like with representing the ions in solution? Well, in solution, you're going to have 1 calcium ion, 2 pluses. You're going to have 2 chlorides. You're going to have 2 potassiums, and you're going to have a sulfate. Right? Those are all aqueous. On this side, you're going to have a solid, some kind of solid, this calcium sulfate. You're going to have 2 potassium ions and 2 chloride ions. Okay? Plus the calcium sulfate, solid. Okay. So the black part is solid. Whenever you see that black as a result. So if we look at the ones that have the black, right, that means that, and notice the way this is set up. This A references this part up here, this top part, right? And B references this one, okay? So if it has solid, we can look at B, C, and D only. B, C, and D are good candidates because they have solids in them. Then we look at the ratios, the stoichiometric ratios of B, C, and D. B says we have 1 calcium and 2 chlorides. Yep. Plus 2 potassiums and 1 sulfate. B looks good. It looks like it represents that one. But look on the other side. 2 potassiums, yep. 2 chlorides, yep, and a solid. So B looks like the best one. It has the stoichiometric ratio as given in the equation and the products. All right, do we have any more marked out? Yeah, we have this one. Oh, we're going to identify some chemical reactions. All right. Okay, 103. Use the following choices to classify each reaction given below. More than one choice may apply. All right, if we have cesium plus fluorine yields cesium fluoride, we have a synthesis reaction. All right. We also have elements going to compounds. We have an oxidation reduction reaction. Okay. There's no oxygen, so it's not combustion. Okay, so we have A, oxidation reduction. We have C, synthesis. You can't have a synthesis and a decomposition at the same time. So A and C are correct answers for 103. 104. Let's see. Sodium sulfate, lead 2 nitrate yields lead 2 sulfate solid and sodium nitrate still in solution. That is not just a double displacement, that is a precipitation reaction. But did we transfer electrons in any of those? The answer is no. The ions are exactly the same on both sides. We had no change in oxidation state. It's a precipitation. It's not an acid base, and it's not an oxidation reduction. It's only a precipitation. That's the abbreviation for precipitate. 105. All right. How about this one? Ammonia plus oxygen is nitrogen monoxide and water. Oxygen. This is a combustion reaction, which automatically means it's oxidation reduction. What else? That's it. Oxidation reduction, combustion. It's not a synthesis. It's not a decomposition. 106. Okay. Sodium plus nitrogen gas is sodium nitride. That's a synthesis. That's not one of our selections. But we do have elements going to compounds. That's oxidation reduction. It's not an acid base. It's not a precipitate because we're starting out with a solid. All right. So the only one that works is oxidation reduction. Rule of thumb, element on one side, compound on the other, that's oxidation reduction. 107. We got mercury liquid plus oxygen is mercury 2 oxide. All right. We got elements on one side, compound on the other. That's a redox. We got oxygen. That's a combustion. Right? But there's not a precipitation. Right? Which one do we have access to? Redox, combustion is not mentioned. It's not acid base. It's not a precipitate. So oxidation reduction is the only one that's mentioned. We can know what the classification of these equations would be, but if that answer is not in the group, then you can't select it. 108. All right, we have gallium nitride decomposes into gallium and nitrogen gas. Decomposition, definitely. Okay, what else? We've got compound on one side, elements on the other. That's oxidation reduction. Okay, we got a compound into elements. That is, well, decomposition, we already mentioned that one. Okay, so A is redox and D is decomposition. It's not a combustion, it's not a synthesis. These two are valid. About 109. We got C2H3O2, which is acetic acid. And we got cesium hydroxide, acid base. Definitely. There's no oxidation reduction here, and there's no precipitate, right? Some acid-base reactions do produce a precipitate, but this is not one of them. So this is only acid-base. See, we're going to do 110 also. Yep. Let's see. We got carbon plus oxygen is carbon dioxide. That's a combustion. A redox, and a synthesis. All right. What selections do we have? Oxidation reduction, yes. Combustion, synthesis, A, B, and C. They're all valid descriptors for this reaction. Let me see. I better make some room now. $111. Let's see. Nitric acid, sodium hydroxide, that's acid base. Simple. Acid base only. We have 112 also. Yep. Okay. 112 says potassium bromide plus silver nitrate produces a solid silver bromide precipitation. And that's the only one. It's not acid base and it's not redox. Right? You check your charges, check your oxidation states, you find that nothing has changed. Only precipitation. $113. Calcium plus hydrogen is calcium hydride. Okay. Oxidation reduction? Definitely. Let's see. Synthesis? Yep. And it's not acid base. And the only one that's in there that we know of is oxidation reduction. It's not acid base, it's not precipitate. 114. 114. Let's see. Zirconium plus oxygen is zirconium oxide. That's a synthesis reaction. It's an oxidation reduction reaction. And it's combustion. The only one we have to select there is oxidation reduction. That's it. 115. We've got zinc plus hydrochloric acid yields hydrogen gas and zinc chloride. All right. Zinc is in a compound on the product side. It's an element on the reactant side. This is definitely redox. Okay. It's also a single replacement reaction. And that's it. It's not an acid base. It's not a precipitate. The only one that's available that we've selected is redox. So you have to go with that. . All right, 116. Yep, we're still taking them all. 116. Let's see, we've got sulfuric acid and barium hydroxide, acid base. And is there a precipitate? Oh yeah, there is. In this case, we do have a precipitate. So we got those two. All right, B is acid base, C is precipitation. This is a precipitation reaction that's also acid base. Let's see. Zinc bromide and silver nitrate precipitate silver bromide. That's the only one. It's not an acid base. It's not oxidation reduction. We don't change any of the oxidation states or charges. So that the precipitate's the only one for this one. 118. Yes, we keep right on going. C3H8 and oxygen. Combustion. Yeah. And it's also oxidation reduction. Okay. It's not a synthesis, it's not a decomposition. So A and B will satisfy 118. 119. Let's see, we have phosphorus plus oxygen is P4O10. That is a combustion. All right, a synthesis and an oxidation reduction. All three. It's not a decomposition, so it's only A, B, and C. Actually, 120 is the same. Right? 120 is a combustion, oxygen, synthesis, yep, makes a compound, and redox. So this is also 120. 121. Let's see what we got here. Mercury 2 oxide yields mercury and oxygen. This is a decomposition. Definitely. Decomposition. What else? Element on one side, compound on the other. This is an oxidation reduction. Okay. So A and D, it's not a combustion, it's not a synthesis. So A and D are the best answers. 122. I'm hammering these pretty good. How about hydrochloric acid and lead 2 hydroxide, acid base? Produces a precipitate also. So this is redox, this is acid base and precipitate. Acid base and precipitate. 123. Looks like a synthesis to me. 123. Synthesis. And redox. Those are the only two I can come up with. A is oxidation reduction and C is synthesis. That's a good answer. 124. We're going to split water. This is a decomposition. Decomposition. And a redox. Okay, A and D. Okay, there's a balancing equation. There's another one. Okay, we've got several to practice with. Which one did I select? Probably one down here somewhere. Well, maybe I'm looking for a real hairy one. We want the complete ionic equation for barium hydroxide and hydrochloric acid. Let's see, are there more than one? Is there more than one part to this? Nope, just that part. Okay. So let's make room. All right. Number 136. We want the complete ionic equation for barium hydroxide. Barium is a 2+, hydroxide is a 1-. So we need two of these. And this is aqueous solution. And then hydrochloric acid, right? Yep. Hydrochloric acid yields barium chloride, which is soluble, I believe. Let me check to be sure. I'm pretty sure it is. Most chlorides are soluble. Barium, yeah, that's soluble. Plus water. Okay, let's balance this thing first. One barium's okay. Chloride, we need two chlorides. So now we have two hydrogens and two hydroxides makes two water. Okay, the complete ionic equation is going to be this barium ion in aqueous solution plus two hydroxides, right? Plus two hydrogens plus, that's aqueous, plus two chlorides yields one barium plus two chlorides plus two waters. Okay, there's your complete ionic equation, and we can't reduce it any further because there's only one of these. That's the complete ionic equation. Now, what would be the net ionic equation? We got barium on both sides. We got chloride on both sides. Right? And we have hydroxide, hydrogen makes water. But this is 2, 2, and 2. We would reduce it to OH minus plus H plus yields H2O. That's the simplest whole number ratio. And this is the net ionic equation for any acid-base reaction. Let's see. Oh, I skipped that one, didn't I? How about this one? Yeah. Oh, we want molecular, complete ionic, and net ionic. Okay, we're going to do the whole ball of wax for this one. 138. Let's see if I got time. Let's see, let me check it out. See if I've got time. If I'm able to finish this. Yep. This is the last one. Okay, so let's take this word problem, 138, and write the molecular or the formula equation. Okay, it says aqueous solution of copper 2 nitrate. Copper 2 nitrate. Right, so we need two of these, aqueous. And all nitrates are soluble. And then the second one is sodium hydroxide, which is soluble. All right, and that yields sodium nitrate and copper 2 hydroxide. OH minus, that means we need 2 of these. And sodium nitrate. That's aqueous. We look this one up, we find that it's a solid. Look that up in your chart. Okay, now let's balance it. Should be fairly easy. 2 nitrates here, we need 2 nitrates here. 2 hydroxides there, we need 2 hydroxides there. 2 sodiums, 1 copper. That is the formula equation. Okay. Now, complete ionic. So we're going to take this copper 2 plus, it's in solution. 2 nitrates. Okay. 2 sodiums. And 2 hydroxides. Then we're going to have our solid plus 2 sodiums and 2 nitrates. Okay, that's the complete ionic equation right there. Now, what's the net? Well, let's see, what's on both sides? Copper 2 plus? Nope, it's in a solid. Nitrate, there you go. That one's out. And 2 sodiums? Yep. Okay. So our net equation is Cu2 plus 2OH minus and CuOH taken twice. There you go. That's your net ionic equation. And that's it. Let's see. We got that. We got the polyatomic ions. We got your chart. And we should have helpful hints for balancing equations. All right. And we got a periodic table. Okay. So all of that will be on the exam available to you. All right, I'm going to scroll back to the top and we're done for the day. All right, so this is Tuesday, next Thursday, which was listed as review day. I did the review today instead. What I will do is Zoom this class from my office. And if you want to Zoom in and ask me questions, or we can cover any kind of problems you have with the course, then that's the time to do it. Next Thursday at 9 o'clock, I will be Zooming from my office.